Alright, so what I think we're going to do here is we're kind of going to do a post-mortem here. So we've done the nitrophenol here. This is what's remaining in the distillation pot, and it's got a little bit of liquid with it, but it's got a big solid chunk in there, and I think that that's the Para Nitrophenol, so I'm going to try and separate that. I've got some of the organic mix here, which I'm going to analyze using GCMS right there, right? And then also, I'm going to be taking a look. So this was the aqueous phase that had the nitric acid in it that separated the organic phase from that produced what I used here for distillation. So I'm going to look at this with GCMS, and then this is my aqueous wash that came from rinsing and cleaning this. So we're going to take a look at this as well and see what happened and what kind of other things we created out of trying to do the synthesis of the orthonitrophenol. So that's the plan, and I'm going to try a little prep here and see if it works. I found a paper, don't know if it's going to work, but we're going to try. Alright, I got a bunch of this set up here, so I've got the procedure tells me that I need to add 200 mils of water, distilled water, into here, and then I need to add in some charcoal, which I have here, and then I have to get this boiling for a minute or two, which is why I have this set up here, and then I'm going to take the hot liquid as it's boiling and then filter it down into the beaker here. And I'm going to be using a coffee filter here because it's just going to be gravity filtration, no vacuum filtration or anything like that. But it has to be done while it's hot, and supposedly this will decolorize this, and then we should end up with a solid product after it cools in the beaker. Alright, that's got the water in there. I've added in the decolorized charcoal, and now we just got to get it boiling. So, let's get it going. Alright, it's been going for a few minutes here. Got a nice little glove on to protect me from the heat. I think it's time to go. It's actually really difficult to get a hold of. So while it's hot, ugh. Alright, whole thing's been poured in. Looks like absolute hell. But we'll see what we get. Oh my god. I don't see this working. Oh jeez. Well, but that's it. Alright, so the gravity filtration was okay. I'm trying to clean this out right now, just because it's disgusting. Bunch of nasty goop in there. Problem is, I've got this here, and it still has all this crap in it because the filters I was using weren't all that great. So I'm going to pass this through a vacuum filter that actually has a 0.2 micron membrane, and then I should have a very clean solution that goes down there, and then I'll pop that in the fridge and we'll see what we get. That's the plan. Alrighty, so it's the next day. We have got the black stuff that's still remaining in here. I was curious about this. Very curious about this. So I've kind of kept that in the original distillation pot. But then I decided to pull the other thing out of the fridge here, and look at this gorgeous, absolutely beautiful pile of crystals. Oh my lord, that's something to behold. Wow. So I'm going to vacuum filter that, that's for sure. I was kind of doubtful, but I guess all of the Para Nitrophenol was really in here, and that sample prep I found online actually seems to have worked. Amazing. Amazing. Alright, got the P nitrophenol. I've already got this tear it out with the weight of this, so we'll see what we got. .6. It's actually pretty good. Huh. I'm surprised. Okay. Just killed the vacuum. I would say that worked out quite well. I don't know what that little guy right there is, but for the most part, those are some pretty crystals. Now I just got to get that pulled off, dumped onto here, finished drying. I think we did it. Okay. Just because I'm curious, I took the filtrate that produced the crystals, and I'm going to try and evaporate it a bit. I know that rotary evaporation of water is it's kind of a waste of time, but I'm going to do it anyway, and I have some concerns that it's going to foam, so I have my bump flask here. It's got this little tube here with those little holes in it right there that'll allow the vacuum to be pulled, but if any of the liquid bubbles up and tries to travel up the neck and over to the distillation receiver, it'll all get caught here. So I'm going to get some ice in this and get this running, and we'll see what we get. Alright, so we got the black goo that was remaining at the bottom of the distillation pot. So I've taken some of this and I put it in solution with some acetone, and it looks like it still has some of the charred up goo and junk in it, but that's okay. I'm just going to see what I can see. So I have this at a concentration of 10 milligrams per milliliter. The reason that I use that as kind of my reference is because I used to run a lot of GPC, gel permeation chromatography, and everything's done in milligrams per milliliter. So I figure, what the hell, I'll still stick with that frame set because it works in my head. So I did the dilution down to that concentration, then filtered it into here. This is my GC vial, and this is then going to go into here, into my liquid auto sampler. So what this is going to do is I'm going to run a blank of acetone, because whenever you're doing chromatography, it's always good to run blanks. And then once I do that, I'll run a blank or two, and then it'll run this, and I'll set it all up in a sequence on the computer. So I'll set it up, it'll run, and then we'll come back and look at the data. Alright, so I'm getting set up to do the GCMS, and I'm going to be doing it on the aqueous phase that was from the main reaction mix. So this had the nitric acid in it, that then phase separated from the nitrophenols, and I'm going to be taking some of this aqueous phase and analyzing it using GCMS. Now, what I'm going to be doing is I'm not going to be taking a syringe and drawing it up and then, sticking it in the inlet and injecting it. What I'm going to be doing is I'm going to be doing something called thermal desorption with chemical trapping. So what I'm going to do is I'm going to take a drop of this liquid, about a microliter, and I'm going to place it in this holder right here. This is a quartz tube that has quartz wool in the top of it. I'll inject it into that quartz wool, and then I will take my sample and I will drop it into this little cell here. Now what's inside of that cell is that little chamber right there that's also made of quartz, and it's got a little wire around it. It's kind of hard to see, but that is a platinum wire that then is resistively heated to the appropriate temperature. I'm going to go to 200 degrees, and then it's going to go from this side into this here. This has an oven inside of it that has a bunch of switching valves and things like that, and then it'll also go over to a chemical trap. That's basically just a little piece of pipe with a chemical in there called 10X. The reason I'm doing this is because I don't want to inject water directly into my GCMS. it's not necessarily a good thing to do with this method, and I'll explain why at another time. But the reason I'm doing this is because the volatile components that come out of this that go into the 10x trap that's over on this side, the 10x will not trap the water, but it will trap, I believe it's your C5+. So I'll see a lot of the volatile compounds, they'll be trapped there, then they'll be focused and directly injected through this transfer line here into the inlet and into the GC, and we'll get a full chromatogram of what we got. So that's what I'm going to be setting up. I'm not going to record it, but I'm just going to use a syringe, a regular GC syringe like this one here. This is a 10 microliter syringe, and I'm going to be pulling up 1 microliter into here and then hitting go. Alright, so it's done running, and as you can see, this is kind of the coming from the switching valve here, but all of these here are individual peaks that come from the sample, and we can do a quick integration. We can take all those compounds, these are all of the integrated compounds right there. We can do a library search, and we can go down one by one and say that is nitrophenol there. We've got another one, 2,4-dinitrophenol, 4-nitrophenol, 2,6-nitrophenol, cyclohexid, whoa, okay. Got some other stuff going on there, not really sure what that's all about. But yeah, quite a bit going on there. Now I'll just do the next sample. Alright, now we're going to be doing the aqueous phase. That was the wash of the original nitrophenol that I made. So we're going to be taking the aqueous wash that had been through the vacuum filtration. We're going to be doing the same thing that we just did before, and we're going to see what we get. Alright, so if we remember, I had the aqueous phase that went through the filter. That's where we caught the para nitrophenol, and I put it on here and rotary evaporated it to where I got a lot of the water out. The reason I didn't use evaporation on like a crystallization dish or some kind of beaker or something like that was I wanted to try and use this to try and prevent oxidation. So if I do a vacuum distillation, you're just going to be constantly pulling a vacuum, and you won't be, heating the sample and then having air blow across of it with a fan or anything like that. So then what I was trying to do was I was trying to concentrate the solution, and then I was going to take that solution and put it in the refrigerator, because then I'm going to be decreasing the volume of the dissolving solvent. In this case it would be water, and then I'll decrease its solubility by making it colder in hopes that maybe if there is more para nitrophenol, it would drop out of solution. And the morning after says that that was correct. Look at all that. That's crazy. So I guess I'll do another vacuum filtration and get all that separated. Awesome. And before I forget, I forgot to mention this last time. Some of y'all might be wondering what this weird thing is on top here. All this is a little valve here that you can open and close and produce a little bleed line here. And normally you can attach another line here to add pressure, and you use this to adjust head pressure on top of a chromatography column. So if you're doing like flash chromatography or column chromatography, you can have this on top, and you can adjust the pressure of a positive pressure gas to push the liquid down through the column. The other thing that I like using this for, so this was originally warm, and then I cooled it off. When you do that, if you have a regular stopper in there, like this one here, it can sometimes pull a vacuum because you've then condensed everything because it got cold, and then it'll be really hard to pull out of here. Well, what I can do with this is you can see that this tip here is actually sealing. Well, if there was a vacuum, it's broken now, and then it's much easier to remove this. So that's the reason why I put that thing on there. I've done that before. I think I did in the previous video, and I didn't explain it. I just wanted to explain that here, why I'm doing that. So. All right, we got a second crop of really good looking crystals. I mean, it's just crazy. And all of that came out of that nasty mixture there. I'm not sure if I should care about that anymore. But I mean, this is really gonna up how much I actually have. So I'll have to add that to what I measured before. Because they look really good. Alright, I think I got them all dried out. Time to get an updated weight here. Hot damn. Another gram. How about that? And then this is what I just filtered this morning. It's still really good crystals. I just haven't broken them all up yet. And I want to do two things. So one, I want to compare this right here, which should be the Para Nitrophenol, with the orthonitrophenol that I've already done. And I'm going to do that using FTIR, infrared spectroscopy. The reason I'm going to do that is because infrared spectroscopy is very sensitive to the change in the structure of materials with regards to isomers. So you get ortho, meta, and para. If you have a great example of this is xylene. So if you had ortho, meta, and para xylene in mass spectrometry, you would see a lot of the same mass spectra. They look very similar, especially if you're using just a single quadrupole mass spectrometer. But with FTIR, because you're looking at the conjugated bonds and you know how those interact with one another in the structure for xylene, you can see the difference between ortho, meta, and para very easily if you can get an individual spectra of each one of those. So I'm going to try and do that, and I want to compare this with the ortho product, and then I want to compare this is my distilled product, with this here, which is the second level of precipitate that I did after evaporating some of the water, and see if they're similar or different at all. That's the plan. Alright, I got the spectra loaded in for what would presumably be the Para Nitrophenol, and we are going to search it against the database and we'll see what we get. How about that? 4-nitrophenol, also known as Para Nitrophenol. And I'd say that's a pretty darn good match. Love it. Alright, and just to drive home the point I was trying to make about the infrared spectroscopy, so this top one here, that is going to be the orthonitrophenol. And then the para product is right below, and you can see that there are some distinct differences in the spectra. And I can give you a little bit different look at that. If we slightly overlay them, you can see all these little differences that distinguish these two spectra from one another, which is really cool, the fact that you can do that. That's why I love this method. It's fast, and it's fairly definitive, especially on rather pure products. Alright, and here is a comparison of the two different precipitates that I got. So this black one is the first precipitate that I had whenever I did that first round of cooling down that liquid and doing a vacuum filtration. This other one up here is the second round after doing the rotary evaporation followed by vacuum filtration, and they're very similar. There are some slight differences. I think you can see that kind of right here. That little shoulder might be a little different. This peak is a little bit more prominent here, but for my purposes, for what I'm trying to do, yeah, you can see it a little better there. It's just not that much of a difference for me to really be concerned. So I'm gonna combine those two fractions, and I don't know, maybe later on I'll do a recrystallization. Just not at this moment. So, fun fact: if you just take the filtrate from trying to isolate that para nitrophenol and you evaporate it, it looks like that. I mean, it's not it's not clean. It still has crystals in it. I'm not going to do anything with this, but it's still pretty cool. Didn't think it would do that. I just thought it was going to be some kind of goo. How about that? Alright, so the first thing that we're going to look at here is going to be the GCMS analysis for the black liquid that was remaining in the distillation pot. And this was after we distilled out the orthonitrophenol, and this is what was remaining. So I just wanted to take a look at this and see exactly what was in that nasty goop. Now it's probably not going to be everything, because there's a limit to the amount of material that you can get into the gas phase that then needs to travel to the mass detector. But we'll see what we can do. So first thing here, this is actually the solvent peak that I used. I used acetone in this case in order to dilute the sample, because you have to have the sample in a pretty low concentration compared to, you know, some benchtop analysis like FTIR, because a mass spectrometer is a very sensitive detector. But we'll go down the list here. So this right here, the 4-hydroxy 4-methyl-2-pentanone, is actually a contaminant that's coming from my acetone. I actually just need to redistill this stuff and clean it up. The malic anhydride is not a contaminant from the acetone, so that's from the sample. Benzoquinone, phenol, a very small amount of phenol. And then we have the orthonitrophenol, and the integrator kind of chops the peak here. So as I'm going down, by the way, you'll see the numbers switch here on the screen. So I'm going to go down the list. There is the orthonitrophenol, and it just chopped the peak up into 3 bits, just because I didn't really mess with the integrator all that much. I just did this really quickly. And then the next peak we have is hydroquinone. And then the next major peak is going to be the para nitrophenol. So there is some of this, actually a pretty significant amount of this, left in the pot. One of the things that is an indicator of the concentration is going to be the peak height, but more so the peak area. So if you're looking at the overall area under here, this is a pretty fat peak compared to this one. The other thing that's going to affect this is, really just some compounds give you greater signal than other ones. As you get higher molecular weight, you get a little bit less signal unless you start messing with some parameters in the mass spectrometer, so that's kind of how that works. I'm not sure about this one. This might be from the sample, I'm not sure. And actually this right here is a contaminant from a completely separate thing that I've run. So one of the things that is kind of the pain in the butt with all chromatography is sometimes you get carryover, and I was trying to clean this out of my system and I just couldn't quite get it out. So this is actually the 3rd time that I've run this sample, and this one is still in here. So anyway, we'll keep going down the list. That wouldn't surprise me if it came from the reaction that I've done. Same thing for this one, because I didn't see these compounds in the sample that this came from. And then yeah, we just have some more of these fun guys here. So yeah, we'll go on to the next sample. Okay, so here we're going to be looking at the aqueous phase, that phase separated from the organic phase after doing the initial reaction. So this is the aqueous phase that probably still had some nitric acid in it. And you will notice here that I don't have a big fat solvent peak at the beginning of the chromatogram. What I have here is this here, and actually all this is a little bit of a pressure fluctuation that happens in the inlet of the gas chromatograph, and that occurs from a switching valve that comes from the thermal desorption system. So if you remember, with the black sample, or the black liquid, I diluted in acetone and injected in the system. With this sample, it was placed into a sample holder, heated up, collected in a 10x trap, and then thermally desorbed to the GC. When that happens, you just get this little pressure fluctuation right here. So anyway, going through the sample, we've got a little bit of the orthonitrophenol. You can see that right here. And then we have a 2,4-dinitrophenol. So that's actually in the aqueous phase. So I would suspect this molecule here is a little bit more polar if you look at its structure, and that's probably why it partitioned into the aqueous phase. We've got a little bit of the para product. So it seems that the ortho and the para product really did phase separate quite well. So it shows a kind of a low solubility in the aqueous phase. And then this little guy right here. So we're looking at kind of a little bit going on right there. And that is a 2,6-dinitrophenol. So that's the nitros are in the ortho position right there. So then we go down over to here, and these, so when you're going this direction, you're going from smaller molecules to larger molecules here, higher molecular weight over on this end. And if we look at these peaks here, and I can show you a head to tail here, so this is the mass spectrum from the sample. This is from a NIST database, and then this is kind of a head to tail is what this is called, of comparison between the two. And this one, I'll just go ahead and read it out because I'm a glutton for punishment. What is this? 2,5-cyclohexadiene, 1,4-dione, 2,5-diphenyl. So this is actually 2,5-diphenyl, 2,5-cyclohexadiene, 1,4-dione. I don't know why it chops the first part of it up and puts it at the end there. And this has been, multiple integrations on the same peak, so you're going to see the same thing there. This one has not been identified because I have set my library match factor to a score of 70. This is on a scale of 1 to 100, and I typically don't like matches below 70%, but we can just try and match this one real quick and see how decent the match is on the head to tail. I mean, it wouldn't surprise me if something similar to this structure was in there, but I don't think I have anything that's chlorinated in my sample. Yeah, I don't think so. However, this right here, which is the last major peak in the profile, which is the 4,4-hydroxy biphenyl, that wouldn't surprise me if something like that was in the sample, and I can compare this against the NIST database using some other software, but I think this is more than enough here. Again, this is the aqueous phase from the initial reaction that was separated from the organic phase that was then used for the distillation. Okay, so now we're dealing with the aqueous wash that was phase separated from the orthonitrophenol that I distilled. So this is distilled water that was in the presence of the ortho product. Ideally, it would be separated from the para product because it should not have been azeotropically distilled out of the distillation pot. And what we can see here is that the first compound, which is not a very high signal to noise. I mean, previously we were way up here roughly to see how small this is here. But if you look at this, it's not a very large signal, so there's not a whole lot of this in the aqueous phase. Or at least that's what this suggests. Now this is a qualitative thing, this isn't quantitative in any way, but it does suggest that the majority of the ortho product was removed from the water that was distilled out of the reaction. So it does show that we should get a high recovery out of this. The next thing that I see here is, again, this kind of product, which it's not outlandish to assume that this is somehow in that phase, but I didn't see anything else that was really in that fraction. So that steam distillation really is an effective way to separate this product here, the 2-nitrophenol, or the ortho product, and it does leave the water relatively clear and clean. Okay, so this is going to be the last one, and I've done this a little differently than the other ones because I wanted to show kind of the difference here. Is I have the aqueous phase that was separated from the precipitate of the para nitrophenol. So if you remember, I had all this organic stuff that was remaining in the distillation pot. I diluted it in water and then added the decolorized charcoal, boiled that mixture together, and then did a gravity filtration. That cleared up the water. I did another vacuum filtration, and then the para nitrophenol was precipitated out of solution. The remaining aqueous phase was then evaporated. It was left in that beaker that had all of the some crystals remaining, and it also had kind of a off color, kind of brownish red color in it. That's what this solution is. Now if you look at the x-axis, you'll see it doesn't start at 0 minutes. It starts at 7. And you don't see that solvent front anymore. The big broad solvent peak is not here. The reason that I've done this is to show that when you do this properly, and you know when the tail end of your solvent peak is, you can delay when the mass spectrometer turns on, and that saves the filament, which is essentially the resistively heated, same as a light bulb filament in the mass spectrometer, and it saves the life of it, extends the life of that part, because those can be expensive to change and they're kind of a pain in the butt to deal with. So anyway, when we go through this one, we're going to go through compound. This is all of the integrated peaks overlaid. You go to list mode here, and you can go down the list. So the first one is 3-hexene 2-one. Maybe that's in there. That's a very small peak here, so if I kind of blow this up, you can see there's another peak here. The integrator caught that, and that is acetic acid butyl ester. Let's go back up to full view. The next one, again, I think that this is just from me. This has got to be a contaminant. Either that or this is what is causing that red color. I'm not real sure. I haven't done my research on this compound. Then we have this fun guy here. Let me double check that mass spectra. Nah, I'm not real sure that's the right match, but we'll leave it for now. I'm not sending this report to anybody. I am not saying that. That might be in there. What is this? 2,6-dimethyl 6-nitro 2-heptene 4-one. Sure, why not? Another one of those guys. Hydroquinone, which we saw previously, and then the Para Nitrophenol, or 4-nitrophenol. So there is some of that remaining in the aqueous phase. It's not a tremendous amount, I don't think, but again, it's not quantitative. This is kind of a finger to the wind qualitative assessment. But this is what was left over after precipitating this product out of that aqueous phase. So it's a good way to try and understand these complex mixtures. When you have things that are really complex, it's good to have some chromatography on your side. Okay, and here is all of the different things that I've analyzed with the GCMS, all stacked one on top of the other. They have the same x-axis. The y-axis is a little different. It's just scaled to the largest peak in each one of the chromatograms. So this was the black liquid that was separated from the original reaction mix with the acetone peak here. This was the nitric acid aqueous phase that has the thermoabsorption peak here, and then you have all these other peaks here. This was the aqueous phase that was separated from the wash of the orthonitrophenol, and then this was the aqueous phase from the wash of the para-nitrophenol. So a little bit of everything. If you overlay them, it looks like a nightmare. So we'll keep them like that. And yeah, I think I'm going to end this video with kind of a oh feeling, because I think that's funny. And yeah, if anybody liked this, please like, subscribe, send me some comments, give me some ideas, and thanks for watching.